In section 8.2, we're going to add one more thing on, and that is the plus C. This plus C is going to take your graph, and it's either going to move it up or it's going to move it down. The number in the front, which in here is represented by A, is still going to either vertically stretch or vertically shrink, otherwise horizontally stretch, and reflect it as well if it's negative. So this is what we learned in section 8.1. We're adding on the plus C to translate the graph either up or down. So what are we going to learn today? We're going to learn how to graph those functions, and we're going to learn how to solve real-life problems involving functions that are in that form. So how do you graph it? Well, here we go. When this value is greater than 0, that means it's a vertical translation C units up. So basically, if this number is positive, that's how many units you translate it up. So the green represents if it goes up. If it's a negative value, if C is less than 0, that means your graph goes down. Now here's what's really important. It looks like the green right here is actually wider than the red or the blue. It's not. We could actually take this red line, or this red parabola, and slide it up, and it would exactly fit over the blue. And the same thing, it would fit exactly over the green. It looks that way because we're not extending it. If I extended the blue, and then I extended the green, you would actually have the same graph. So it's more of an eye trick than anything. That these are all the same. They're just either translated up if it's positive, down if it's negative. You'll notice that the axis of symmetry is always x equals 0. So in example 1, let's graph the function g of x equals x squared minus 2. All we're going to do is take our parent function x squared, and we're going to slide it down 2 spaces. So if you did make a table of values, x and g of x, if I plug in -2, -1, 0, 1, and 2, that'd be 4 minus 2, 1 minus 2, 0 minus 2, 1 minus 2, and 4 minus 2. If we graph this, and I'm going to graph the parent function too. We do not have to, but I am. It would look like this. Here's your blue graph, g of x, and the parent function has just been slid down too. So it says compare it. Well, we could say both graphs do what? They both open up. Both graphs also have the same what? They have the same the axis of symmetry. What else do we know? Well, we know the vertex of the first one is 0, 0, but of G, it's 0, -2. So the vertex actually went down 2. And then why is that? Because it's a vertical translation 2 units down. So now let's look at example 2. Now just by looking at it, what do you think is going to happen? We have a 4 in the front, and we have a 1 in the back. Just by looking at this, I can tell you that because this is 4, it's going to be narrower. It's going to be vertically stretched by a factor of 4. It's still going to face upward because it's positive. But then your entire graph is going to go where? It's going to go up 1. So if I was to make a table of values, if I plugged in -2, -1, 0, 1, and 2. Now I'm just picking any 5 values that I want. So if I plug in -2, let's see, that's 4 times 4 is 16, that'd be 17. If I plug in -1, that'd be 4 plus 1, which is 5. 1, 5, and 17. Now I'm going to graph this. And if I do graph this, I'm going to count, you can count by anything you want, but this graph counts by 2s. Well, what happened here? Notice what happened. The blue graph is your g function. It's much narrower. It also went up 1. So what can you tell me? You could say both have an axis of symmetry of x equals 0. You could say they're both facing upward. You could say that the graph of g is vertically stretched by a factor of 4. You could say it's also narrower, and that's fine as well. And then you would say that the entire graph is what? It's translated up 1 unit to a vertex of 0, 1. So example 3. Example 3 gives us two functions. Now these two functions are f and g. It says describe the transformation from the graph of f to the graph of g. Then graph both of them. So if we're looking at A, what does it say? It says that the function g is taking the function f and subtracting 7. So we can take the function, which is f of x, equals negative a half x squared plus 2. And it says we have to subtract 7 from that. So because it says to subtract 7, g of x is going to be taking the negative a half x squared plus 2, which is the f of x, and subtracting 7. So that would give me negative 0.5 x squared minus 5. So there's the first part of step A. The function is g of x equals negative half x squared minus 5. And actually, we just solved B. B is right there. Write an equation that represents the function g. We just did that. Now, if we graph this, if we graph both of them, it would look like that. Function f, which is represented by the black parabola, has just been moved down 7 units to where the y-intercept is here of negative 5. That's it. So solving a real-life problem. Now, I'm not really concerned about the solving a real-life problem. What I am wanting you to look at, though, is the zero of a function. You are now going to be asked to find the zeros of a function. The zeros of a function are when that function is equal to 0. For example, y or f of x is equal to 0. The zero of a function is an x-intercept of the graph. So, you're probably thinking, what in the world does this mean? Well, you've actually done it already, and you probably don't know you've done it. So if I gave you this, x squared plus 9x plus 20 equals 0. That's finding the zero of a function. Except now, what you're doing is this. F of x equals x squared plus 9x plus 20. So what you're doing is plugging in that 0, and then you're factoring just like you did last chapter. So here there's no GCF. I'm going to get two binomials. What two factors of 20 am I going to use? It's going to be 4 and 5. And that will give me my value of negative 9x as my middle term. We solve these, and our two answers are x equals negative 4 and negative 5. Here's what this means. When you graph this, 1, 2, 3, 4, so negative 5 and negative 4, this graph is going to cross through these x values at negative 4, negative 5. So whatever you get when you solve and factor this are where the parabolas cross the x-axis. That's how you find your x-intercepts, is by finding the zeros or factoring. You could also graph it and see where it crosses. Our last example is a real-life problem. So let's just look at this problem first and see then what it's asking us to do. We have a function, f of t equals negative 16t squared plus s sub 0. Represents the approximate height in feet of a falling object, t seconds after it is dropped from an initial height of s sub 0, which is in feet. So let's stop there. T stands for the number of seconds. The actual function represents the height after something starts falling. And the starting height is represented by S sub 0. It says an egg is dropped from a height of 64 feet. Here's the person right here dropping an egg. That means I'm going to have the function f of t equals negative 16t squared plus 64 because we are 64 feet above the ground. After how many seconds does the egg hit the ground? Well, I want to find t, but when the egg hits the ground, what's the height? The height is 0. If I wanted to know 1 second, you'd plug in 1 here. If I wanted to know 5 seconds, where would it be? You plug in 5 here, but it's 0. Negative 16t squared plus 64. After how many seconds does it take to hit the ground? Wait a minute. We can graph this. If you graph this, you're going to have a graph that looks like this. We're going to start at 64. It'd be upside down since it's negative 16. And it go, and it land on the ground right there. Now your domain here has to be greater than 0 or equal to 0 because you can't start anything less than that if it starts at 64 feet and after 0 seconds. You could find the x-intercept. Absolutely, that would work. You could also plug in a t-table and plug in 0 to this equation and you get 64. After 1 second, you'd be at 48. After 2 seconds, it would be at 0. So you know that after 2 seconds, this hits the ground. It takes 2 seconds. But wait a minute. We just learned last chapter how to solve a quadratic equation equal to 0. Step 1, take out a GCF. The GCF would be negative 16. And if you took out a negative 16, you would get t squared minus 4, and then equals 0. Since we know negative 16 just stays there, t squared minus 4 will be t plus 2, t minus 2. If you solve this, you get 2 answers, negative 2 and positive 2. Negative 2 doesn't work since we cannot have negative seconds, so 2 seconds is also obtainable by a graph and also solving the quadratic equation. So then it says B, suppose the initial height is adjusted to k feet. How will this affect part A? Well, we could say that if k is greater than 0, that means the egg will take more than 2 seconds to hit the ground. What does that mean? Well, that means if we add more to hit the ground. If we change the value of k, that means we're actually adding on more feet. So it's going to take longer to hit the ground. However, if we shorten the distance, then the egg will take less than 2 seconds to hit the ground. Once again, we have negative 16t squared plus 64. If this value increased, it would take longer than 2 seconds to hit the ground. If this value decreased, by whatever we decrease it by, it'll take less than 2 seconds to hit the ground.